Yes, thank you for introduction. My name is Rokhmanova, and today I'm going to present you the work about transformation of terahertz wave polarization via transmission through a finite slab of layer superconductor. 2 days ago I was presenting you a work that also deals with layer superconductors. So for those of you who heard my presentation, I would like to say that this work differs in that here we were studying linear waves and studied cases when transformation of waves occurs. So the outline of my work is following. At first, I'll describe what are live superconductors in general, or remind you, and give you the main perspectives to study them, and formulate the main problem this work deals with. And then I will show you the results for two geometries. Layer superconductors are periodic structures in which thin superconducting layers about 0.2 nanometers are separated by the thicker insulator layers about 1.5 nanometers and are electrodynamically related to each other by means of intrinsic Josephson effect. The main feature of such materials is the existence in them so-called Josephson plasma, which is an example of solid-state plasma where charge carriers are represented by electrons and copper pairs. This plasma is strongly anisotropic. The current along layers is the same as in bulk superconductors, while current across layers is of Josephson nature, and this anisotropy allows propagation of Josephson plasma waves, which is very interesting for various applications since they are of terahertz range. Here I would like to say about some designations in layer superconductors. Waves that has no Z component of electric field is called ordinary, and waves that have no component of magnetic field is called extraordinary. So I will use this designation further. And here in field, the coordinate system is chosen in the following way. As you remember, the electromagnetic field inside of layer superconductor is defined by the Gauge invariant phase difference phi of the order parameter and can be defined from the coupled-Sine-Gordon equations. Coupled-Sine-Gordon equations in continuous limit can look as following. We can rewrite this equation in the following wave equation form. The relation between a vector potential and electric and magnetic field is given by the standard equations, and scalar potential is assumed to be equal to 0. Current density along layers is the same as in bulk superconductor, and current across layers is of Josephson nature. Using this equation here in this problem, we will describe field inside of layer superconductor. And there were a lot of works that were studied Josephson plasma waves in layer superconductors, but they studied them for infinite samples. This work deals with finite sample of layer superconductors that is placed inside of vacuum waveguide. So we have two vacuum regions and one region filled with layer superconductor. And we study two geometries when layers are perpendicular to the waveguide axis and when they are parallel to it. Also, I would like to remind you that we will mostly deal with waves of TE and TM polarization. Waves of TE polarization are those that has no component of electric field in the direction of propagation, and the M waves are those that has no component of magnetic field in the direction of propagation. And it turns out that for the first geometry, incident TE wave generate inside of layer superconductor only an ordinary wave, and the M wave generates inside of layer superconductor only extraordinary, and polarization doesn't change. But for the other geometry, the same waves of TE and TM polarization generates a combination of ordinary and extraordinary modes that leads to some transformation of polarization. Also, we'll have a look on polarization that is matched with layers of superconductors, that's to say with the z-axis. So let's have a look on the first geometry. Here what I would like to mention is that for TE waves, they are attenuated, and the M waves have a narrow range of frequency where they are running. And this equation is important because it defines critical frequency from which actually starts propagation of waves in a waveguide. So using continuity conditions for tangential components of electric and magnetic fields, one can obtain transmission coefficient for the M waves for running wave and for attenuated wave, and for the E waves the expression will look the same as for attenuated wave. This figure shows transmittance of the superconductor for this geometry versus frequency of incident wave. As you can see, for running wave, the transmittance is non-monotonous. There are frequencies where transmittance is equal to 1, and the steps between peaks is getting wider with frequency increasing. And for attenuated wave, the transmittance is much smaller than for running wave. This figure shows transmittance versus thickness of the layer superconductor. As you can see, for attenuated wave, this dependence is decreasing exponentially, and for running wave, the transmittance is periodically equal to 1. It corresponds to geometric resonance, which is completely the same as resonance transmission of a particle above a barrier in quantum mechanics. And now let's have a look on the second geometry, where more interesting, where transformation of polarization occurs. So for waves of TE and TM polarization for small enough samples and for frequencies that are close to critical frequency, it is possible to convert incident TE wave into reflective TM wave, and incident TM wave into, I made a mistake. Incident TE wave into transmitted TM, and incident TM into reflected TE. And also, it is possible to find some transformation of polarization on dependence of the M wave on transmitted amplitude of the M wave. And also for waves modes that which polarization each is matched with layers of superconductor, it is possible to convert polarization for samples that is small enough and for frequencies that are close to critical frequency, and it is also possible to convert polarization for frequencies that are not close to critical frequency, and so incident wave incident wave of such polarization can be converted into transmitted wave of such polarization with small admixture of the other component. So that's all that I wanted to say. So the main idea of this work is that for a certain condition, a layer superconductor can convert polarization. Thank you for the attention. Any questions? Okay.
So I have some questions here.
Oh my God.
No. I just, you are speaking about terahertz waves.
Yes.
Just, what's the, to have an idea, what's the wavelength of these terahertz? Just to compare with the usual optical waves we are used to.
It's frequency 10 in 10 power. Yeah.
Okay. And so the wavelength?
It is millimeters.
Millimeters.
Yeah.
So
like thickness of paper.
Okay. And so in this kind of layer system,
yep.
usually you have some special effect where the signal is transmitted, not the signal, the phase is transmitted at the speed higher than the speed of light. And do you have something like that, this?
I haven't studied this, so I'm not sure that I can like answer it in the right way, but I'm not sure.
So because that's something which is always a bit interesting and tricky. It's not the speed of the wave packet, because it's impossible to go higher than the speed of light, but at least that, and that's always interesting to have such a system with okay.
Thank you.
Other comments, questions?
The question, can you compare the value of the critical current in your system and in system without insulator layers?
Can you repeat your question?
Can you compare the value of a critical current in superconductor in your system with insulator layers?
You mean critical current in these Josephson junctions?
Yes. In superconductor with the junction and without.
But if you don't have this insulator where is Josephson junctions, the tunneling? Yes. Yes, so if you have the superconductor, where is this Josephson junction?
Okay.
Really, I don't understand that.
Okay. So, maybe so that's the end of the session. Thanks again.
Yeah, thank you.